All right, 7.2 is going to be about exponential growth and decay, and we're going to use those functions to help us solve differential equations. So our essential question is, how do you write and solve differential equations? And let's start by remembering what a differential equation is. So a differential equation is basically just an equation where we've already taken the derivative of a function, okay? So it's an equation that is the derivative of a function. So let's say, for example, the one that they give us in our book is they show the derivative of p with respect to t would be equal to some constant times the actual function p. Okay, and so to solve this, what you're going to want to do is you're going to want to find an equation for p as a function of t. Okay, so solving means find an equation for p as a function of t. And there's this k here, and this k is called a proportionality constant. Right? So it's basically a constant, okay? It's some number, okay? And it will describe the proportionality. So we're going to use this to work on the exploration that I handed out to you in class, okay? So our objective is to write and solve a differential equation for the amount of money in a savings account as a function of time. When the money is left in a savings account, it earns interest equal to a certain percent of what is there. The more money you have there, the faster it grows. If the interest is compounded continuously, the interest is added to the account the instant it is earned. Okay, so you probably are thinking to yourself, oh yeah, once upon a time I knew a formula for that, like PERT. Okay, so we're going to now start with number 1. For continuously compounded interest, the instantaneous rate of change of money is directly proportional. Okay, so we know it's directly proportional. That's why we know that we're going to end up using that proportionality constant to the amount of money. Define variables for time and money and write a differential equation expressing this fact. Okay, so that's what we're going to do. So I think it's pretty obvious that we would probably use t to represent time and m to represent money. So m will be the money, t will be the time. And so now I'm going to write a differential equation. I'm basically going to write one that looks just like this with a proportionality constant. Okay? So we know that the amount of money is changing with respect to time, right? So we can rewrite this we can write this as a differential equation. The derivative of the money with respect to time will basically be equal to, it's proportional to the amount of money that's in there. Okay, that's m. So we've got this proportionality constant, k, times the amount of money that's actually in there. Okay, and we know that k is going to be our constant. All right, the next thing we're going to do is we'll separate the variables in the differential equation in this problem above. Okay, then integrate both sides with respect to t. Then we'll transform the integrated equation so that the amount of money is expressed explicitly in terms of time. So I'm going to get my m's on the same side. So right now m is on the right-hand side, but dm, the change of m, is on the left-hand side. So I'm going to bring this m over here by basically dividing by m. So I'll have 1 over m dm, and then I'm going to multiply dt to the other side. So I've got that constant times dt. Okay? And now let's remember that this constant here, if I didn't have any t's at all, so if for example, if I had t to the 0, then it would just be that constant, okay? So from here, I'm going to, I think it says to integrate. So transform, let's see, then integrate both sides with respect to t. Okay, so now that's what I'm going to do. I'm going to integrate both sides with respect to t. So taking the integral of both sides. So this is 1 over m, so I know that I'm going to have ln of the absolute value of m. And then on this side, with respect to t, well, that's a constant right there. So now if I'm taking the integral, I'm going to now have a t plus some other constant, plus a c. Okay, and from here, then, I've got a logarithm. I can rewrite this as an exponential, right? So I can have the absolute value of m equals e to the kt plus c. Okay. Moving on to 3. The integrated equation, let's see, let me make sure I answered this part. So actually, let me go back to 2. Transform the integration so the amount of money is expressed explicitly in terms of time. Okay, so that's true. M is a function of time. All right, so now let's move on to number 3. The integrated equation from problem 2 will contain e raised to a power containing 2 terms. Write this power as a product of 2 different powers of e. One that contains the time variable and one that contains no variable at all. Okay, so you want 2 terms. Now notice what you have. You have a base raised to a sum, right? So we can rewrite that as the product of those 2, right? So e could be raised to this times e raised to the c. Because if you remember, a long time ago, once upon a time, if you had the same exact base, then you could rewrite this as a to the m plus n. So we're basically going to work backwards. We're going to take this and we're going to break it up so that I have 2 separate bases. Okay, and what's going to be important here is to realize that if this is an absolute value, that means that my output could be both positive or negative. Okay, so I'm going to write this as m equals positive or negative e to the kt times e to the c. So this one does not contain a variable at all. Okay. Now remember, like I said in the beginning, this is a compounded continuously function. So this probably has a little bit of, should look a little bit familiar to you, right? So compounded continuously is PERT. Look what I'm having here. I basically have some initial amount that's being multiplied by e raised to something time. So moving on to number 4, you should have the expression e to the c in your answer to problem 3, which we do. Explain why e to the c is always positive. And I think the best way to think about this is, what is e? Well, e is going to be approximately 2.718, right? So we can say, and if you think about like the graph of e, for example, so the graph of e, or e to the x, has this asymptote at the x-axis, right? So for any time, even if that time is negative, or for any input or for any number, even if that input is going to be negative, that's just going to give us a smaller number, right? It's just going to be the reciprocal of this. So basically, you're going to always going to have a positive output. So if you take any positive number and you raise it, so a positive number raised to any power is always going to be positive. Right? And e is a positive number, approximately 2.7. Okay, moving on to number 5. Let's replace e to the c with a new constant. We'll just call it c sub 1. If c sub 1 is allowed to be a positive or a negative, explain why you no longer need the positive or negative sign that appeared when you removed the absolute value in problem 2. All right, well, I'm going to go ahead and start by replacing e to the c with c1. So if c sub 1 is positive or negative, then it's basically just going to change what we originally had here. Or it's not going to change, it's going to take us back to what we originally had here, right? Because think about it, if your constant is negative, this flips the graph, right? So when you think of like the graph of e to the x, well, now if you multiply it by some constant that's going to be negative, that's going to give you the reflection in the x-axis, okay? So we can say that c sub 1 can be positive or negative. And then let's think about what that means. So when m is less than 0, then we'll know that c1 will be some negative input. Or when m is greater than 0, then we know that c1 was some positive constant. Time equals 0. So we'll use this initial condition to evaluate c sub 1. So we'll plug this information in and we'll get an amount for c1, or c sub 1 I should say. So $1,000 is the amount of money when time equals 0. So I get 1,000 equals, well, k times 0 is going to be 0, and this will become 1 then. So 1 times c1, or I know that c1 will equal 1,000. So I can rewrite myself an equation using this where I plug 1,000 in. And we'll put that first. Okay, so moving on to number 7. If the interest rate is 5% per year, then the derivative of money over the derivative of time, or with respect to time, will equal 0.05 times money in dollars per year. What then does the proportionality constant, in problem 1 equal? Sorry, I couldn't read that one. All right, so I'm getting the derivative of money with respect to time equals 0.05 times money. So thinking about this, just maybe comparing it with this, right? Those are basically the exact same structure. So what does k equal? Well, k is just going to be the coefficient of m. So we know that k equals 0.05. How much money will be in the account after 1 year, 5 years, 10 years, 50 years, 100 years? Do the computations in the most time-efficient manner. So what would be the most time-efficient manner? Well, I think using our graphing calculator and maybe the table feature would be the most time-efficient manner. So I'm going to rewrite our equation. We know that k is now 0.05. Oops, I forgot the 1,000. Put 1,000 here times e to the 0.05 t. And I think using our graphing calculator would be the best way to do this. So let me pull up my Wabbit. You guys go ahead and get your graphing calculator. Alright, so I'm going to do this in my graph part. We'll put 1, 2, 3, and then I'm going to multiply that by e raised to the 0.05 times my variable. And then what I want to do is for 1 year, 5 years, 10 years, 50 years, 100 years. So I'm going to do my table set. I'll start at 1, and then why don't I go up by 5? That'll at least give me the first 2, and then I may want to change it after that. Okay, so after 1 year, let's see. So I'll just kind of figure out a way to, after 1 year, I'm going to have, it looks like 1,051 and 30 cents. After 5 years, oh, I increased by 5. That wasn't good. I needed to increase by 4. Oh, well, that's all right. I'll go to 5, and next time I'll increase by 4. No, by 5. That'll get me to 10. Thinking out loud here, sorry. Okay, so after 5 years, I'm going to have $1,284. After 10 years, looks like I've got 1,648 and 70 cents. What else did we need? We needed 50 years and 100 years. So I can see that I can get to 50 pretty quick, or I can go back and change it. So it looks like 12,182. Let's see. Oh, there's some cents over there, and 49 cents. And then I'm going to go down a few more and end up at 100. So 14,000. Nope, 148,000. $148,413.16. The last part of this asks how long would it take for the amount of money to double its initial value. So the initial value is 1,000. So we're just going to set this equal to 2,000. And you have a couple ways that you can solve this, and one of them is to go ahead and divide both sides by 1,000. And then maybe, t. And then maybe ln both sides, so take the natural log of both sides. So you'll end up with ln of 2 equals, and that will allow me to, actually these will undo each other, so I'm just left with 0.05t. Okay, and then divide by 0.05. Okay, and when you do that, you're going to get that t will be approximately 13.863 years. Another way to do this, let's say you were allowed like a graphing calculator, well then it would be to put 2,000 in as one of your y values, and then 1,000 and put this function in as like a second y value, and then figure out where they intersect. So that's another way. I find that sometimes plugging things into a calculator takes a little bit more time, so sometimes that's not the quickest way, but if the numbers were really hard to work with, or it wasn't really clear like how to go about solving this, using a graphing calculator would be really, really, really helpful. And then I'll let you answer number 10 about what you learned as a result of doing this exploration. And then we're just going to do another example together, a short one, just something that's very algorithmic, meaning how do we go about doing this. So just to remind you one more time how to solve a differential equation. So we're going to say solve the differential equation. Okay, and so let's just take that example that I used up here. Okay, so here's the first step. What you want to do, and it follows basically what this exploration had us do, right? The first thing that we did was we got our dm and our m on the same side, and then we integrate it. Okay, so that's what we're going to do here. So the first thing we want to do is I'll bring that p over, so I have to divide, right? So that's 1 over p dp, and then I'll bring that dt over here, so it's k dt. Then I'm going to integrate both sides. Okay, so I get, well, this part right here becomes ln of the absolute value of p will equal, now remember that's a constant, so if I'm doing the antiderivative of it, now I'm going to have a variable, and it's going to be t, because that's what we've got over here is with respect to t. Okay, plus some constant. Okay, now we're going to basically rewrite this in exponential form. So my base is e, will give me the absolute value of p. However, the absolute value of p, oops, did I do that right? Yeah. The absolute value of p basically means that p could be either positive or negative. So now I'll use my properties of exponents to break this up. But then remember, this is going to be some kind of a constant. So instead of using e to the c, which will always have to be a positive constant, I can get rid of this positive or negative here if I just redefine this as some constant, just c to the sub 1. Okay, so I'm going to call this then e to the kt times c sub 1. Or a better way, in a way that we're used to seeing it, c sub 1 goes in the front. Oops, I'm off the screen, aren't I? There we go. Sorry about that. So I redefined e to the c as any constant, which could be positive or negative. And then this order we're not really used to seeing it in, so I just went ahead and rewrote it.